Hi, this is Neural Search Talks, post-CIR conference, in person from the beautiful courtyard at the William Gates building at Stanford. And I'm here with Omar Khattab, last year PhD student here at the computer science department. Welcome on the show, Omar.
Yeah,
Great to have you.
Thanks for having me.
So Omar is well known for a number of things, in fact, both ColBERT and the DSPy framework. And today we want to zoom in a little bit into the DSPy framework and kind of the recent advances in that. So at CIR in Washington, D.C., you gave a very nice talk in the Large Language Models Day. So large language models have kind of taken over CIR, right? And you gave a very nice talk in this session about this sort of new paradigm that DSPy started, right?
Yeah.
Can you tell us a little bit about what was the gist of the talk?
Yeah, for sure. So, the context of a lot of this work is that, language models have made it so easy to build things we just couldn't build before. We couldn't imagine building before.
Yeah.
But a lot of us are quickly realizing that these are really impressive demos, but when it comes to building systems we want to put in front of users, systems that are reliably part of bigger architectures or things that are scalable, things that are reliable, our demos only go so far, and they don't really permit us to do this. And this really matters in practice because people's ambitions have become really high, and we want to build these systems that are able to do all sorts of things.
They're like the fastest new generation of technology to go from research to production, actually, right?
Yeah, precisely. I mean, and the scope is impressive, and the opportunities are truly endless. But the challenge here is, language models are so inherently, they keep getting better. We just got Llama 3.1 out, there's been a Mistral release, there will be more. But fundamentally, what happens is that these language models are so opaque. They are sort of kind of by design, and this is really what makes them so powerful. They're so monolithic that controlling them in the way that people need when they're trying to build systems is just really hard.
Yeah.
So my work is sort of revolving around how do we build reliable and scalable systems with these language models. And DSPy sort of comes to that with the angle of, well, if you want to build controllable systems, if you want to build systems that you can improve and iterate upon in ways in which you're, essentially more systematically engineering them, then we need to move away from prompting or ad hoc ways of fine-tuning or whatever ways in which we are using this technology towards more sort of principled or more systematic things that look more like programming.
More like classical software engineering.
Or more like classical software engineering, or more like, how a machine learning workflow or data science workflow would have looked, before language models.
Yeah.
But of course, you want to do this in ways that leverage the strengths of these models while addressing their shortcomings.
So I think the core of the DSPy is, on the one hand, this new paradigm, right, where you kind of write natural language programs in a structured way.
Right.
Which also is embodied in a lot of other frameworks of chaining together different agents or modules. But I think the DSPy approach is also very special because it has this optimization mindset.
Right. So the main thing is you don't want to be in the mode of thinking, how do I coerce this language model to do my task?
Yeah.
You want to be
thinking, don't do this, don't do that.
Some of this eventually may be useful or important or not, but these are lower order things. These are like hyper parameters you tune after you build your system.
Right.
But the most important thing is building your system. So setting up the architecture. And the key idea here, or one of the key ideas here, is really these models are really powerful at tasks that they have seen and tasks that are standard enough that they were trained on. And so we can sort of leverage that by building modular systems where these models are responsible for well-scoped individual subtasks, and we compose these modules into bigger systems that sort of just call out to the model to approximate or solve these subtasks individually. And what sort of helps us go from just saying that to actually doing it is a series of programming abstractions or new algorithms that sort of make this whole thing cohesive.
Right.
So like it's one thing to say we want to build modular systems with language models, and then you sit down and you write actual like 5 separate prompts. And it's another thing to build an actual modular system with language models. And so a lot of the progress in the last couple of years, and if you look at sort of systems that really make it into production in a satisfactory way, they're generally like this. It's what we call these language model programs or compound AI systems that are making so many little calls to language models and sort of composing them carefully in code.
Yeah.
And there are essentially 2 ways to go about building this. The standard way is to say, well, here is my system architecture, here is my diagram. I want to build a system that is going to answer user questions, or is going to autocomplete sort of text for people writing code, or is going to do any number of those things. And so I'll have the following modules. And then for each module, you sit down and say, well, my
this
input
is the ideal prompt, and
and you sit with a model.
Exact instructions, like 2 pages. And,
right. You write 2 pages of instructions. You iterate on each and every one of these prompts. And the challenge here is that getting the model to sort of perform the specific task that you want is hard, but it's a lot harder in these compound AI systems because each of these modules has to interact with the rest of the code.
Yeah.
It's not enough that is giving you valid output. It has to give you the output that the other modules expect.
Yeah, there's a lot of dependencies.
There's a lot of dependencies here, and the whole system has to be cohesive. So it is actually not that hard in practice, if you know what you're doing, to get a model to sort of perform a specific task. Writing prompts is challenging, but it's not that challenging.
Yeah.
What is challenging is maintaining a system of several prompts that sort of are supposed to interact in a bigger system.
Yeah.
So DSPy introduces a few ideas in this space. One of those is prompting techniques sort of become essentially meta-programming functions or sort of function generators. So you give them a signature, like a function signature, that just defines the relationship between inputs and outputs. So you say, I want a module that can take questions from users and generate search queries.
Right.
Or I want a function that can take maybe a goal and a set of tools, and maybe I wanted to select the right tool to call. And this is the full description of the interface of the module. Now, how the module gets filled, like that just defines a whole essentially, or defines a kind of an empty, unspecified implementation, but we've defined the interface.
Yeah.
So you can specify many modules in this way, and you can say, well, for this module, I would like it to be implemented in the form of a chain of thought. So that's a particular prompting technique that sort of in practice, people usually sit down and write examples of, here is how the model should reason about this particular type of input to generate that particular type of output. But here we just say, well, for this particular signature, for this interface, I'm interested in getting the model to reason in order to do it.
Right.
For this other module, I have a different interface. Maybe the interface is RAG-like. So take a question, take some context messages that were retrieved in some way, and please answer, give me an answer accordingly. And so that's just an interface. And you could say, well, I want this interface to be addressed through, a program of thought. So a program of thought just means this sort of meta flow where models generate code that gets executed, and based on the execution result, a model sort of generates an output accordingly. And so now we're sort of moving and talking about these interfaces at the level of abstraction that we design these systems at.
Yeah.
And you just write your function, you call these modules,
and then the prompts kind of become hyperparameters within this larger system, right?
And the prompts become parameters in this system. But you're basically just describing your control flow with respect to these modules.
Yeah.
And well, you could think of this as a normal computer program. You're just writing Python, or it could have been any other language, and you're just calling these fuzzy modules, these unimplemented functions that have these fuzzy interfaces. Now the question becomes, how do we, who and how should these functions be filled by? So what's the process that should happen here?
Yeah.
And the most important thing is, well, we do already have a notion and sort of have a lot of intuition about the process of taking high-level code and converting it into low-level code, maybe by generating code underneath, or meta-programming or other tricks. And essentially, it's this notion of compiling the code from high-level language to a lower-level language. Except that the lower-level language here is, how do I take these modules that are specified in a fuzzy way and sort of map them into actual language model calls, which generally means what? It generally means, well, what model should I call?
Yeah.
What are the weights assigned to? Like, are we updating the weights? Are we using them as is? And how are we formatting the inputs into an actual prompt that allows us to call this model? And normally, when you're sort of thinking about compilers or metaprogramming or other such techniques, normally the behavior of the program is well defined. So the behavior, like there is correct behavior and there's incorrect behavior, and sort of there are semantics around this programming language that guard all of this work.
And is that like essential for the DSPy framework that the programmer, let's say the human designer of the flow, actually splits down the work into these tasks? And how does that kind of contrast with maybe sort of the more general agentic approach, where you have a high-level goal and you actually ask an LLM to decompose it into tasks?
Right. So let's finish the thought and then come to this. So in normal compiling, kind of the program is enough to specify what behavior should happen, and then you're compiling because you want to map to a more efficient language, or you want to go from a high level to a lower level language, or whatever goals you have. And so the behavior of the function is kind of well defined, but where you have a lot of scope for optimization is usually efficiency. What we're looking at here is cases where no one actually knows how to implement a function that's supposed to generate answers or generate queries that go into a search engine, and the search engine is supposed to retrieve high quality stuff.
Right.
We don't know what the right implementation is because there is no right implementation. And so the missing element here is asking users or asking the developer, what is the function you're trying to maximize?
Yeah.
Like, give me some inputs, give me some realistic examples of just the input questions that you want to answer, or input documents you want to translate, or input reports you want to summarize, and give me a sort of a guiding metric, some kind of objective that sort of tells me when success has happened, or gives me a reward, or sort of gives me a notion of like good or bad attempts.
And a way to evaluate.
A way to evaluate. So now you've asked, like, well, now the programmer has to specify three things. They have to actually design this system. They have to
break down into
pick the modules, write the actual function. They have to sort of figure out what types of inputs they expect to see. Now, maybe, in many cases, 30 inputs or 50 inputs are enough, but you still need some. And they need to think of what's the metric they're trying to maximize. You might contrast this with much more ambitious approaches that essentially say, just give me an objective in English, like I want to buy a ticket for a flight from San Francisco to DC or something like that. And the system just sort of spawns lots of agents, and they talk and they interact. I think the problem here is we want to enable people to build systems that they can trust.
Yeah.
And for that, we need to be grounded. So language models, talking to language models is an impressive way to generate a very large bill.
Yeah.
But it's not necessarily a reliable way to sort of build it.
Certainly not yet. Right. We've all seen the demos that they can go.
Now, it is always, so the point here is we want to leverage humans and developers and engineers for what they are good at. So they're good at thinking about their problems. We can't replace that. We don't know how to sort of abstract away problem solving in the general sense. This is a much more manageable sort of machine learning problem of like, well, you sit down, you write a simple initial program, you write a simple initial metric, you optimize, you see what the system gives you. You're probably not happy immediately, just like any other system you're building, but you know how to iterate, and you know how to add complexity in sort of increasing levels step by step as you go along. And so we enable sort of people to go back to an iterative development that is sort of grounded in metrics, grounded in feedback. They're collecting data over time. And this is really important. I see a lot of people that like DSPy who sort of use it sometimes successfully, but this is still not sort of optimal, where they kind of write a very simple, chain of thought program or RAG program. They don't think about it anymore. It becomes a black box agent essentially, and they sort of like expect the optimizers to just magically figure things out for them. That's not how it's supposed to be used. It's essentially a programming language. You are solving your task, not the system.
And optimizing is part of your loop.
Exactly. The system is just making sure that the parts that you're not best equipped to deal with, which is figuring out these sort of parameters, is delegated outside, but you're still the person designing the system.
Right. So before we go further into sort of these ideas about optimization and the more recent developments is in DSPy. I just want to go actually way back.
Sure.
Because you're now in your final year here as a PhD student, and you didn't start your project working on DSPy, right? You were essentially working on information retrieval problems and wrote ColBERT and all these things. So what was kind of the eureka moment when you thought, wow, this is a cool idea. I need to change directions. I need to start working on this.
Yeah. So the process here was I worked on ColBERT in late 2019, my first year. And if you think of ColBERT, what's really cool about it is that, we're using BERT as a language model. So maybe some context is ColBERT is a retrieval model that looks quite a bit different from other retrieval models in the neural era. Most models that use language models or transformers for search, they kind of use the transformer as an encoder that you give it a document and it spits out a high dimensional vector, and you do the same for queries, and basically similarity is a dot product.
Yeah.
And that's really cool because we know how to scale dot products up to massive data sets. It's very fast, but it leaves a lot of quality on the table because now you're basically asking models to compress a long document or a long passage, a couple hundred words at least, into this one high dimensional vector. Very hard.
Yeah.
Especially hard when you're trying to generalize from a domain you trained on to a domain you didn't train on.
Yeah. So you avoid that with ColBERT, but how does that lead to DSPy?
So you avoid that with ColBERT, and you avoid that with ColBERT by essentially building this modular structure, modular system in which the model is used, to produce representations that are not just atomic, but they're actually sort of decomposed into pieces that capture, individual tokens, and the system uses them in an interesting way.
So was that already the seed of this modularization idea?
I think it's certainly consistent with it. But the interesting thing is, after working on ColBERT and sort of seeing a little bit of that modularity, although I wouldn't say that was, a crisp idea at the time. It was what I worked on next was sort of what was called at the time open domain question answering. So nowadays we call that RAG, but this is sort of the general problem of how do you answer questions when the answer is not supplied to you in a context. And
maybe in a complicated multi-hop reasoning kind of
a very important special case that is multi-hop, where basically the problem here is you're asked a question, and in order to answer it, you resort to retrieval. So the model doesn't remember everything, and even if it does remember everything about the past, the world keeps changing, and you want systems that can cite their sources. And there are so many reasons that sort of motivate us to build systems that are now modular. So now these systems are going to retrieve first, and then use those retrieved elements as actual text that goes again into the model, and the model, downstream generates answers accordingly. So I built a system called ColBERT QA. And so a lot of the work there sort of thinks about retrieval and generation, but you immediately see the notion of modularity directly here, where, we are saying you have a module that is responsible for generating answers, and you can optimize it for that, but you have a separate module that's optimized for actually finding relevant sources, and you can optimize it for that. So then sort of I worked after that on a system called Baleen that was, as you said, for multi-hop sort of reasoning. And multi-hop reasoning is kind of an interesting, it's kind of a problem that is designed to encourage a specific sort of solution, but that sort of solution is a lot more general than specific benchmarks seeking this. So multi-hop question answering is basically saying, what if you want these systems that are generally retrieval based to answer questions that require combining information that's usually not found in any specific context? So language models, what makes them so powerful beyond, Google search is something that we've had for decades now. So what makes language models so powerful is that they can sort of synthesize in their parameters and in their activations during execution, kind of a lot of nuggets from different places.
Right.
So if we are going to move towards a modular design where we have a retriever and a generator, well, we better be able to also answer these types of complex questions.
Yeah.
So a system like Baleen, what it does is it sort of takes complex questions, essentially it breaks them down into representations of simpler questions, it retrieves stuff, and then it actually reads those documents it goes back into the system retrieves more stuff that sort of fills in the gaps of knowledge that it's accumulating, and it's using all of these as intermediate clues to sort of build up a bigger puzzle. And so that is now really an instantiation of a truly modular design that, you know, has Baleen in particular. It had like 7 or 8 models at least. So models that were retrieving, and essentially in doing that, they were kind of producing queries. Models that were summarizing. So like, you know, you retrieve 100 documents or you retrieve 20 documents, but you can't possibly, you know, keep accumulating those documents. So you take these 20 and you produce a summary of what is actually relevant here. And then you sort of generate more queries and you proceed. And so like, you know, this process has modules.
So you were trying different things, and then you thought, this is not a great programmer experience. I need some sort of language to declaratively iterate over these different systems.
But so much else was happening. So this was before GPT-3 had public access. And so like GPT-3 was, you know, not instruction tuned yet. It was really not competitive with systems we could fine tune. And so Baleen was a system that was fine tuned. And so it had, I can't remember the exact number, but I wouldn't be surprised if it was 9. You know, you had to train 9 different models together between the retrievers. I think we had to train 4 retrievers and at least 1 re-ranker and at least 1 summarization module, and then an actual question answering module.
All separately.
But but for it to work well, you had to train them on data that was in domain enough. Like, you know, you can't, if you're going to train a re-ranker, you want to make sure that it's trained on the distribution of outputs you're getting from the retriever that will be deployed with it.
You need this end-to-end optimization effect, basically.
You want to approximate an end-to-end optimization, but certainly it's actually hard. It is too hard to actually make it end-to-end trainable, and so approximated in a workflow. And this is really hard because basically most of these modules are trying to do things that are intuitive and make sense, but no one will give you data for these. The data sets that support, there are data sets like Hotbot, QA, or Hover. Hover is really cool, that support multi-hop question answering or multi-hop reasoning workflows, but they certainly could not have anticipated all the possible modules you will build. So no one is going to give you training data for all of these individual modules. And so the difficulty of building a system like Baleen, I mean, in hindsight, it's pretty clear what modules you want, but like, how do you generate the training data that will allow you to train these modules well together? So Baleen was a specific, you know, here is a very, very powerful but specific strategy for generating the data and getting these modules to work together. I remember back then I was still thinking about models, not programs. So when you think about models, you say, well, and this is still the pervasive way, like the overwhelming majority of the language model community, the NLP community, and beyond in general, you know, the way we think of these systems is that we have a bunch of models. So when you think of it this way, you know, it's really hard because now you have basically all these scripts that are training models, and then you're just connecting these models as an ad hoc thing at the end of the day. So the DSP and DSPy sort of motivating kind of goal was to basically say, what if the focus is shifted from the model to the system? What if I'm not building 9 models in Baleen, but I'm building the Baleen system?
Ad hoc scripting them together, but top down. Really,
let's actually think of building the system itself, the Baleen architecture itself, and then the modules become very similar to layers in neural networks. Like if you're sort of building ResNet, or you're building kind of, you know, AlexNet, or you're building a transformer BERT or something, you know, it has 12 layers of attention. You don't think of, I mean, you just compose these layers. You
want to have the right abstraction.
You want to have the right abstraction where you're composing these layers, and you want to specify some kind of objective, and you want to have some optimizers that are doing the right thing under the hood, and, you know, maybe better optimizers come along in the future. But at the end of the day, the idea is you want to have a data-driven way of sort of learning how to fill in the blanks or how to update the parameters of these systems. So a system like Baleen that was, you know, several thousand lines of code thinking about models could be expressed in general in like 15 lines of, well, I have these, you know, 9 modules. It's a lot of modules, but each of them could be 1 line that just tells me, well, I should take this and give that. And there should be a function that's like, here is the loop that composes them, very simple Python. And as long as I can specify a right objective, and as long as I can have optimizers that take that objective and kind of reflect it into the choices made in the parameters of the system, then we will be able to successfully iterate on these systems. And so you could go into a system like this, remove a module, put in another, change the language model that's underlying all of this, and change that. Now, that was not possible at the time of Baleen. It was not possible because to synthesize data here, it was hard. So it was a manual process where you needed a lot of basically heuristics to connect the pieces of the system together. And the heuristics were very problem specific. What happened in late 2021 was we started getting language models that actually worked, in the sense that instruction tuning started emerging, and we got things like DaVinci 1 and DaVinci 2. They were very slow and expensive and unreliable. But basically, you started to see that few-shot prompting or instruction prompting could give you systems that were unreliable, but could do just about anything you could describe in English.
And like few-shot prompting came up really big, right? Like just provide a handful of examples.
Yep.
And so I've talked to a couple of people before this interview, and they're like, DSPy, great new paradigm to build these kind of systems. And a lot of people still think it's about like selecting the examples only, right? That's like a preconception from the original work, where the optimizers were very good at that. So a lot of the benefits came from selecting the right examples. But you have progressed so much further, right? So more recent work, I want to go a little bit into these optimizers. So what kind of things can you optimize, and how does it really like play along with the power of these very recent language models and the way they can follow instructions and be very like precise about those instructions?
Right. So the most important thing is, if you're building a framework, DSPy or otherwise, that needs people to give you examples of these modules, you're not going to go very far. And the reason is, the whole point is to enable people to iterate on these system designs, which means that they'll take out modules and they'll throw them away, they'll add other modules, and they want to be able to essentially recompile and see what happens. They need to be able to iterate. Now, examples that are needed or necessary are at the level of the function that as a black box. What are you taking in as an input, and what do you expect about defined output? The internal structure should be entirely sort of independent of the data that you're building, because the data is about the task, the problem, and the program is about your solution. So there's a bit of a separation of concerns here. So what demonstrate search predict, the precursor of DSPy does, the demonstrate step, is the notion of, can we use the actual program that you've given us to generate examples? And if we could generate those examples successfully, can we basically then look at selecting among them? So that was sort of in the original DSP. And that is far more powerful than most people sort of realize. I mean, obviously, I'll discuss more recent optimizers, but this is 2 years old. But basically,
ancient by today's standard.
Yeah, ancient by today's standard. But this is incredibly powerful, because what you're saying is, I'll take the inputs you give me, I'll sort of make a guess about the initial sort of configuration of every module, which means I'm going to keep the parameters of the model unchanged, and I'll just guess an initial template that sort of says, the signature you gave me, I'll convert it to this prompt. And basically, you can then sample through your system by running the function, and every time there's a language model call, you can sample output, and you can sort of chain them together, or sort of let them run your metric, and basically do things like rejection sampling. So like, if the answer is sort of liked by the metric, you keep it, you keep the whole trace, otherwise you throw it away. Or things like best of n, if you have many, you could run it many times and keep the best one if the metric is continuous, things of that sort. These traces now, what they give you is for free. You have examples for every module along the way. And the question is, are they correct? Are they like, useful?
Is it like a test case that is actually representative of the core distribution?
A lot of people look at this, and then they say well, I mean, you generated some reasoning, then you generated the search query, then that search query led to some passages being retrieved. Those passages were then used to generate an answer in a RAG system. Was any of this intermediate steps correct? And once you start thinking of these as parameters, it doesn't really matter if they're correct per se. Well, I mean,
as long as they're helpful.
As long as they're helpful. And so not every example is equally helpful.
The space becomes so high dimensional that, or exponentially explosive, that you don't really have an idea of where where the helpful support points are, right?
Precisely. So the first set of optimizers were all about how do we generate enough of these examples and how do we figure out which of their combinations should be plugged into each module.
Right.
And the surprising thing is, it is actually really hard to beat random search. So if you generate a lot of these examples and you try basically random subsets of these bootstrap demonstrations is what we call them, you can get really far, because basically the average trace you're generating is not very effective. But for some reason, some of the more extreme ones, when you plug them in, you see the average quality, it's very powerful. But the amazing thing,
maybe just to make it a little bit more tangible for our viewers. So what does random search in this case mean? Because you're actually like tweaking the prompts, right, with this search process. So can you give an example of like what would be a step in that search process?
Right. So the first thing is you have a program, you make an initial guess in the system about what the prompt should look like. So that's, there are two ways. Basically, it's either just a template that takes your signature and plugs them in, or it's you ask a model, just give me an initial.
So let's say for RAG, you have something like, here are a bunch of retrieved documents, find the answer to them, stick to the facts only.
Well, that's too much work. It might just be if your template, if your signature is, I'll take a question and some context and generate a message. You tell the model, I have context, question, and I'll take context, question, and generate an answer. You tell the model, given context and question, generate answer. There's no customization.
So how do you kind of evolve that into more sophisticated instructions? So
now the idea is you can take the question inputs that you have, run them through the system, meaning it will run through this prompt and run through the retrieval and run through the rest of the program. And then you have a way of filtering, was this actually correct? Like, did I get the right answer? This allows you to keep those input outputs of every module as demonstrations if the process is successful. So the random search is basically saying, well, I have so many of these. If I grab 5 of them randomly and plug them into this module and plug those into that module, and then take this as an updated program under the hood, and I evaluate it, I validate this whole thing, what do I expect it to perform like? Do I see that it's performing on average pretty well, or do I see that it's performing even worse than the zero-shot version or otherwise? So you're plugging in those examples that you generated. So this is the simplest thing you could do in order to sort of maximize that function, given examples that you're building. But
that's a very predictable dimension of variation, right? You're just
precisely
generating examples which all work, and they just work to different levels of degree, then you select the best one.
And when you look at tasks, this can take you like, basically this random search process in many cases can take you from like 20% to like 50% to 80% on the same task. So what is actually being conveyed by these different combinations of examples is pretty interesting. But the amazing thing is, now that you've built those examples, your toolkit is much bigger, which is what a lot of the, more sophisticated optimizers do. So the first thing that is like pretty easy you could do here is, well, if you generate enough of these examples, you can train the model on it. Like, instead of showing it to the model in the prompt, you can basically go to the model and do supervised fine-tuning, where you say, given this input for this module, this is the output that worked in the past, so you should generate more of that. You could do something like, DPO or such. We don't have that in DSPy. Currently, there's a lot of sort of related ongoing research where you say, well, given this input, this output performed better than that output, and you basically sort of optimize as such. Another thing you can do, which is what MePro does, is you look at those.
Which is your very recent paper, right? It was published.
MePro is like 8 months old at this point, but the paper is newer.
Okay,
the paper was kind of a retrospective of like, let's look at many of the optimizers.
So MePro was kind of introduced in the open source framework, and then later the paper came out.
So we introduced MePro in December, and or at least released it in December, and then we told people about it publicly. I mean, people used it successfully, and then we sort of tweeted and told people about it publicly in March, and then we released the paper on it in June. So what MePro does is basically it looks at those examples and it says, well, how can we get the model to generate examples, to generate instructions that convey the function that these examples are these successful examples are conveying? But it actually goes a lot farther, because it studies the program itself. Like, it looks at the structure of your program and it tries to figure out, what is this program trying to achieve? And what is my module here? What is the role this module is trying to play in the program? What are the examples sort of conveying? And through that, it generates a lot of instructions. And, you know,
so it's like kind of a meta level understanding of the overall end-to-end task.
Right. So trying to understand the end-to-end task and the role of each specific module in it, so that the instructions that generates for each module, you know, language models are really good at brainstorming. They're really good at sort of, there's a really cool paper led by a student here I'm also part of, called Storm. And the name Storm comes from the notion of brainstorming. So language models are sort of really good at brainstorming, but they need to be grounded. You need to give them what to brainstorm around. And the other thing is, you need to filter all of this brainstormed sort of low quality stuff for the high quality occasional things. So Meeper does that exactly. It has notions of how do we ground the language model proposals in the actual context of the program and in the context of successful examples. But then a lot of prompt optimizers almost stop there. They basically have these notions of, let's ask the model to critique, and let's use that critique to generate an instruction. Well, odds are the instruction the model generates is worse than whatever you started with. It's in many cases. So what you want to do is you want to over-generate and you want to test. And the problem here is when you have a program that has 5 modules and you're trying to, you know, think of 20 potential instructions in each, and for each of them, you know, there are 20 potential few-shot sets that we generated. This becomes a massive discrete search space. It's a lot smaller than the search space sort of all possible strings, but it's pretty large. So the nice thing here is that one of the easiest things we can do very successfully is borrow from the hyperparameter optimization land. Basically say like, well, you know, I have a very expensive function to optimize. The function is plug things into my program, run it on a validation set, sort of with some inputs and check the metric. Very expensive. So you want to do what is called sequential model-based optimization. You want to essentially be, in some sense, training or sort of optimizing some external small model that tells you, if you combine these selections, here is what your system will perform like. Here's what the expensive evaluation function will perform like. And
so
then
it becomes a little bit like reinforcement learning in some sense, right?
It becomes like reinforcement learning, but it's a lot more discrete and cheap. In the sense that RL is like, if you're optimizing a policy, really, I think it's almost, in that case, it's somewhere between reinforcement learning and meta learning. So in that case, it's a really expensive and finicky process. But in general, things are inching towards more and more, you know, reinforcement learning like things. And you know, when you're optimizing the weights in a DSPy program by updating, I guess this is a little technical, but basically the DSPy optimization problem is 2 RL problems. One is, how do I update the policy? How do I update the model that's making the choices in the modules? So how do I get the language model, which is operating as sort of my agent or my policy and taking actions, which is generating strings that are part of this program? How do I update it to maximize you know, expected returns? This sort of, when I say something like, you know, you generate those examples and you sort of do rejection sampling and you train it on them, you know, rejection sampling based fine tuning, you know, or expert iteration or star or these types of ideas, you know, that is basically a kind of a poor man's reinforcement learning is one way to think of it, in the sense that, you know, like it has analogies to reinforce and the like. But you could easily see extensions of this that do PPO or DPO or the like as well. Now, of course, the closer you go to things like PPO, the more finicky the whole process gets, because hyperparameters become very important. And, you know, in general, it's currently a process that generally has only been achieved by people, engineers sort of tinkering with them. Can we get sort of reinforcement learning, deep reinforcement learning methods that just work out of the box and use them to build optimizers in DSPy is an open question. I think, frankly, we will be able to, but it's you know, it's still an open question.
I mean, you really like opened up a whole new box here, right? Like,
right.
One of the things that I was thinking about is this quote. I think it comes from somewhere from MIT, which says, a good thesis answers an important question in the field. A great thesis puts a new perspective on the whole field. and an excellent thesis kind of defines a whole new field of research. So I think you're definitely somewhere between those
I hope so.
last two. And so it really seems like you've opened up this kind of new way of thinking about these systems as coherent ensembles of kind of the old Marvin Minsky way of society of mind, where different agents are interacting and is all behaves nicely as a mind, right?
Right, but we get to do that while thinking about it in ways that. So what is the problem with modularity in general? I mean, a lot of old AI was highly modular, and there were systems that were built very thoughtfully. And in some sense, they didn't solve the same problems that deep neural networks solved. And this is something I think about often. So I think you want modularity at the right level of abstraction. So when you think of humans and you think of the way in which we recognize that this is a nice tree, or this is a flower, or this is sort of a dangerous place to enter or a safe place to enter, all these reflexive decisions are happening without pre-mediated planning or without sort of decomposed thoughts. They're immediate. And so I think basically modularity has to happen at the level of abstraction where, like, we've already more or less solved these reflexive system one type sort of.
That's basically the single model kind
That's
of.
basically the single model. And so a lot of the attempts at modularity for some problems, not for all problems, just couldn't get far enough. If you're spending all your time thinking about building parse trees, well, guess what? Humans talk without thinking of parse trees. So that doesn't mean parse trees.
I hope that's true still.
Well, so in some sense that that doesn't mean parse trees are not useful.
I think here on campus there are still few people who who would disagree with that.
I actually don't know. That's I'm not sure. I suspect
at CSLI or something like that.
I think we're all much more aligned. But so I'm not saying parse trees are not useful. I am saying that getting successful parse trees is clearly not essential to successfully mastering language. And in some sense, it ends up being a distraction if you're thinking about modular systems. But being able to sort of divide a complex task like writing a research paper into, well, I need to find sources, I need to draft it first, I need to iterate on my draft, basically having multiple passes and multiple steps is so fundamental that no model will ever train will sort of write general open-ended sort of articles about anything you might think of in one forward pass of a neural network. Now, these sort of recursive approaches might generalize and might sort of, the structure itself might be self-generated by the model, so there might be scaffolding its own architecture, but at the end of the day, sort of like a simple forward pass through a neural network is only really learning things that you have to compose on top, as functions or modules in order to really maximize what you're doing out of these systems. And so that's the bet that DSPy makes. I mean, something that I haven't said in public too many times because I wasn't asked about, but I said it a lot in private talks, is the goal of DSPy is not that you're specifying 5 modules, so we will actually optimize 5 models. It is very possible that you say, I want a retrieve module and a generate module, and I want the retrieve to pass into generate. And under the hood, the optimizer or the compiler decides, actually, I have one of these neural networks, one of these models, that can actually do the two together. And so it will fuse the calls. It's the same thing as what compilers do when you say, I want an add and I want to multiply in the context of a matrix multiplication. And they actually compile it into a single instruction that's multiply and add. So I think the same notion here of, like, models will sort of give us bigger and more coarse-grained and more powerful instruction sets, if you will. And the abstractions, the code we write, will look the same, because smart compilers will go from the level in which we want to describe our programs, to the effective ways in which we want to teach our systems. So I described the reinforcement learning problem that sort of DSPy makes a lot easier because it has those, like, declarative modules. Like, basically, you could have thought of the same RL problem 10 years ago, but the reason it would have been so intractable is that you couldn't have sort of worm started each module by basically taking a signature and guessing an initial prompt and sampling decently successful patterns out of it. So that's a really key thing. But there's actually a separate learning problem, which is kind of a bit a little bit more meta learning on top of it's just really the optimization problem, where you're not trying to learn the policy inside the program, you're trying to learn the policy that decides what choices to make in order to optimize the system. And so here, this is a much more expensive problem, because you're not just getting a signal from every data point. You're actually getting a signal from basically, in principle, like, the entire validation set or samples of it. But this is a much more powerful space, because, now you can kind of see the whole process on top and basically learn across tasks, and say, like, learn across models. Like, hey, I'm optimizing for GPT-5, but I have seen 20 previous models, and so I can kind of like, well, this is a bigger model, it's a more powerful model, and so like I can extrapolate.
And you could have like really this a system, an ensemble of many different models, maybe which have different strengths or which are at different levels and can kind of support each other and all that.
Right.
So I'm curious to hear your thoughts on this sort of end-to-end learning, right? Where the main problem is kind of credit assignment, right? Like which model gets updated. And so there was this recent paper also come out of here called TextGrad, which was clearly inspired also by your work. Is that kind of the direction where you see this thing going? I thought it was kind of metaphorical. Like it introduces kind of backpropagation of gradients notation, which was not really like mathematically correct.
I think they're definitely thinking in the right level of abstraction. I've seen some people sort of dislike, some prominent people dislike the analogy. I think it's an amazing analogy. I think they did a really good job conveying it. I think the abstractions are great. So let's see. I think sort of the notion of backpropagating, errors,
across this whole like undifferentiable system
in language is an idea that's here to stay. I think it's a good idea. I think on its own it's pretty weak, and the reason is, to backpropagate errors, you need to know what the errors are, and to know what the errors are, you need to ask a model what went wrong. And I think the problem is models are very good at sort of giving you canned, general, diverse in principle, hopefully, if they're not badly tuned, suggestions, or they're good at brainstorming,
but not at like
but if you want to be precise, and you want to fix the actual problem, models are not there, and I haven't made up my mind if they will get there or if this is a very fundamental type of limitation. I think something about it's fundamental, although we can train them enough that like most tasks end up being addressed with precise enough feedback. So the problem here is you're at the mercy of the language model critiquing the right thing and taking that critique to make the right proposal for fixing and to make the right proposal for what to backpropagate up the stack. And that is highly limiting. So what you actually want, and I think where the future is headed, is you definitely need a component where the model is brainstorming actively what went wrong. But then what you want to do is, and we have some optimizers that we've built in here that sort of take this insight and do a whole lot more with it. But basically, you really need to make things driven by actual experimentation. So you're sampling from this distribution of hopefully getting some decent suggestions, but unless you've tried them, you can't trust them. And so this is what something like MePro is really good at. It's good at efficiently exploring many different suggestions without exhaustively testing everything. And I think the moment you start realizing this is the moment you really think of, well, if you're building those systems by hand, there's just no way you're exploring this massive space of like, how do I build examples to use them in my prompts, and then to use them to fine-tune my system, and then to use them to generate instructions and to explore those for models as they come along, and new afresh all the time. It really has to be an automated process. And so I think seeing things like TextGrad is very encouraging to see that other people are picking up this optimization problem and are coming up with creative
it's this kind of paradigm shift, right?
Right.
And nobody knows yet exactly where it will go.
We don't know,
But it's impressive that you kind of inspired this paradigm shift with DSPy. I think that's fair to say. So I want to shift the conversation a little bit more to practical stuff, right? This is all research. It's fascinating intellectual endeavor, but really when you talk about engineering, the code matters. And so you've open sourced DSPy. First of all, I'm kind of interested how open sourcing it and receiving feedback from the community and contributions to the code, how that's kind of influenced the direction that you're taking with this project.
I think what makes this manageable and successful is that most contributors are contributing in a highly modular way. And so what I mean by that is no one is like working at this point, it even includes even me. So no one is really working on DSPy actively. What people are working on are specific parts of DSPy.
Yeah.
So there are the
to make it work for their application. Probably, right?
Well, actually, no. To make specific capabilities or components better. So
Right.
we have the DSPy optimizers team. I mentioned Krista, Michael, Dilara, Josh. So who am I missing? Anyone else? These are the main four. Those folks, they are absolute experts when it comes to how do we do prompt optimization, how do we do weight optimization in DSPy, and such. There are other folks who are sort of responsible for the assertions side. It's a highly sophisticated module we have in DSPy. So that will be Arnav, Shangin, Manish. And like they know about assertions better than I do by a large margin. Yeah. We have folks who are like in the core APIs of the LLMs and the internal abstractions. And so like Cyrus, Amir and Kyle and others. Things related to that here and there by just folks from the community that are just wonderful contributors. I'm thinking Thomas, and others. And so I think what works nicely here is I think our code is in need of a pretty deep refactor, and it needs to be cleaner. But conceptually, the parts of it are super sort of the separation of concerns is effective enough that folks can just say, I study optimization. I don't do signatures. I don't do types. I don't do assertions, but I will focus on getting optimizers to work really well. And I think that's been inspiring because you have those folks who have all these really powerful ideas and they're not distracted by, 10 different use cases that are outside their scope, etc. Everybody's really focused on their individual elements, and they're all motivated by many successful things that they're building.
Yeah. What's your vision for the future of this field? I mean, I know it's very hard for anybody in AI to have a vision which extends further than 3 to 6 months these days, right? But what's kind of your research engine? Because I think you're choosing to stay in academia for the foreseeable future.
Right.
So what's your vision on a research program that you want to pursue?
So I think we are in a place where not 3 to 6 months, but 3 to 6 years is visible. Beyond that, I genuinely have no idea. But for 3 to 6 years,
you're very optimistic.
3 to 6 years, I really do see the shift towards modular systems. I really see a lot of people reinterpreting whatever it is that they learned from things that have so much value and such, but things like the bitter lesson. I think the bitter lesson is fundamental to people familiar with it. Notions of machine learning and building ideas that scale. I think fundamentally the idea from all of computer science is you want to avoid premature optimization. Some people say premature optimization is the root of all evil. And this applies to machine learning just as anything else. Another thing that applies to machine learning just as it applies to anything else is that you really need modular systems. You really need separation of concerns. You really need fast iteration cycles. And deep neural networks on their own give you none of these three. But through notions, in DSPy and through notions similar to them, I think it's pretty clear that they can serve as kind of leaves or modules that we can control through optimizers. But at the end of the day, your program is a program. Your control flow is actual control flow. So what's happening in 3 to 6 years is that a lot of that is really going to become basically machine learning is one thing, and it's really good at learning, but it's pretty bad at composition. And I think the idea that machine learning and programming are going to become the same is an ambitious, but I think very realistic vision, where very few major projects are going to be programmed in anything that is that is not essentially a language model program. So most large programs will have modules that are fuzzy and that are coming from a language model. As a word might not exist, but essentially some kind of deep neural network that understands language as well as other things. Maybe foundation model is a more long-lasting term, maybe not, I'm not sure. But this is a fundamental way in which a lot of people will do that and will not even think that they're doing machine learning. They're just going to be thinking, I'm just writing a system. And so that means that systems will come with metrics, because the only way you can optimize this or compile this is if you define what the objective is. So systems will have objectives. They might not be functions, they might be statements, or what are they called in some other contexts? They might be called constitutions or rubrics or whatever it is. But basically, they will have those statements of purpose. Systems will have a purpose, and they will be optimized accordingly. And the other thing is, from the other extreme, very few machine learning projects will not take the form of programs as well. So if you're building a system, if you're releasing, agents, if you're doing, it will always, people will think first of the function rather than of the models, and they will, models will become, I think all of these are already here. It's just that it hasn't been internalized. So models have become, but they will become more clearly like chips. So if you think of, NVIDIA or other people, AMD and others producing GPUs, most of us building software or building models or doing machine learning, I mean, some people and some academics and some other people sort of are interested in building better chips. And, some of our collaborators do that, and it's very important. But for the vast majority of us doing machine learning, the vast majority is just something that you buy from the experts who keep making it better every year through amazing processes. But it's like, it's kind of a commodity, and whoever is producing the best one, might have a monopoly for a while or might make a lot of money out of it. But at the end of the day, the process is that you're building software, you're thinking of the software, and you just buy the best hardware you can get your hands on and you use it. Language models are basically going to become the same, or foundation models are going to become the same, where really they are commodities. And the vast majority of academics, the vast majority of everyone interested in machine learning will just license them or buy them or download them or whatever it is. And because of languages like DSPy, you just get the latest one, you will recompile your code, and you will expect that it will just work. Now, similarly to GPUs, sometimes your CUDA code that is supposed to be faster on the bigger GPU will actually be slower because somebody tweak
a little bit,
somebody did premature optimization, or is it bad? There was a bug in the compiler. Yes, we will need to fix it. But at the end of the day, the paradigm is that models are a commodity. They are just devices. Software is what matters. Programming and machine learning sort of come together because we need learning always, and we need composition always, and they will get closer. And I think a lot of the hype around general artificial intelligence,
I was just going to mention that,
will start dissipating, and I hope it doesn't dissipate all of the interest in in related things, because I make that joke too often. I think it's becoming old at this point. But I don't work on AGI. I don't believe in AGI, but I do work on API, which means Artificial Programmable Intelligence. So I want people to be able to write code or programs that sort of exhibit intelligence in the applications they care about. It's like general specific intelligence. So it's like general tools for getting people who are motivated. Like, we already have developers, they already can write code, they already can solve problems. What if they solve the problems they care about, and sort of they express the specs of the solutions, or the kind of the declarative kind of scaffolding of the solution, and we're just helping them map that or compile that to machine learning constructs under the hood. I think that is where I see the future headed.
That's great. So I think that makes you a humanist rather than an AGI believer. And I think that's great. I think we need a future where AI systems serve humans and not the other way around. So thanks you for this interview, and thank you for opening up this new direction of research. It's fascinating. We'll see what comes out of it. So thanks for watching. This was Neural Search Talks with Omar Khattab, live from Stanford's Computer Science Courtyard. Stay tuned and enjoy discovery.